Hello everyone, this is Maitreya Suin, and today I'll describe about our work, Diffuse and Restore. So the task of blind face restoration is a challenging task where our goal is to given an input image we want to produce a high quality facial image. But the challenge is we do not know the exact type of artifacts or degradation that is present in the input image. So if we look into literature, there has been many works which uses some handcrafted priors, and very recently we have seen a huge progress in terms of neural network architecture or generative models. To be specific, GAN inversion based approaches take an input image, project it to a small compressed latent space, do some refinement operation in the latent space, and then again project it back to the pixel space using the decoder. Now, although this produces good output of a very high perceptual quality using the adversarial training framework, there are some certain drawbacks. For example, when you are compressing a given input image to a compressed latent space, we we are bound to lose some finer pixel details, which might be crucial for the identity of the version. Very recently, diffusion-based frameworks have outperformed GAN-based methods in terms of perceptual quality. But if we take any off-the-shelf diffusion model, we rarely have any direct control over the recovered identity at the final output. So, as I said, there are two main goals of the blind face restoration task. One is we have to generate a very high quality output image, and also we have to preserve and recover the underlying identity of the person, which is extremely crucial for downstream task, for example face recognition. To give an example, if we are able to generate a very high quality face image but the identity of the person is altered, it does not serve the purpose of downstream face recognition task. So if you look into the literature, typically what we observe is that people use a single network but multiple losses such as reconstruction loss, adversarial loss, or identity preserving loss on a single network. But in our observation, we found that to be inefficient. So instead of using a single network and force it to optimize multiple losses, we separate out these two tasks. One task is of generating high perceptual quality image, and the second task is recovering the identity of the person. So we use two expert network, train it separately, and then we try to combine their output to give us like a single output image. So to start with, we build an IPC network which stands for Identity Preserving Conditional Network. So this is basically an image-to-image baseline for which we can use any standard framework. In our work, we use Suin's transformer architecture. And this network is trained using standard L1 reconstruction loss. Additionally, the main part is we use an identity preserving loss. Now, in our work, what we have observed is that if we keep very high coefficient of identity preserving loss and a very small coefficient of L1 loss, it helps us achieve our goal, which is generating a facial image where the identity specific locations are properly reconstructed, but as the L1 coefficient is low, the network cares less about the other regions. So as the purpose of the IPC network is to recover the identity specific features, this particular combination of these two losses where the coefficient of identity loss is higher serves our purpose. If we look into the output image of IPC network, we can observe that for crucial facial locations such as eye region, nose or mouth regions, it is able to reconstruct those regions pretty well. But if we look into the other regions, for example, the skin area or the hair area, we can observe still there is some blurriness or those regions are not properly restored or reconstructed. So once we have these identity specific features for these particular facial locations, now the task remains is how can we improve the overall perceptual quality of the image. Because for end user, the whole face image matters, not only the identity specific features, which are also crucial for the downstream face recognition task. To address this problem, we deploy our second part of our network, which is based on a diffusion framework. In our work, we use standard DDPREM framework where we take an input image, add some amount of noise, and get a noisy version of that image, and then train a denoising unit to predict the noise or the clean image. Now, instead of using the standard reverse diffusion process where you start from pure noise and run the diffusion process for let's say 1,000 time steps, we introduce some certain changes to make sure that that recovered identity is preserved. So the first change is instead of starting from pure noise, which is used in some of the previous works, we start from an intermediate time step. As in our work, we already have like a baseline estimate, which is the output of the IPC network, and it also has very crucial information about the identity of the person. We introduce some amount of noise to get to an intermediate time step in the reverse diffusion timeline. in our work we use, for example, 200 to 400 time steps, and once we have the noisy version of the eyepiece's output, we start the reverse diffusion process from there. It also reduces the number of time steps required in the reverse diffusion process, and hence it accelerates the whole restoration, the time required by the host restoration pipeline. But it also helps us to preserve the identity to some extent, because we already start from an intermediate stage which has the information from the output of the IPC network. Now the second thing is, what we observe is that even if we start from, let's say, t equals to 400 and run 400 number of reverse diffusion time process, then it is very easy to deviate from the path of the correct identity and go to a different trajectory where the output is of higher perceptual quality, but the identity is slightly altered. So to add an additional regularizer, we use a pretend face recognition network, for example, arc face, and we use the output of the IPC network as like our guiding signal. We take, at every time step, we take the output of the diffusion network and we compare it with the output of the IPC network. And basically we take the feature embedding from the pretend arc face network, we get the cosine distance between these two, and we formulate an face recognition loss which is based upon the cosine distance, and we take a gradient with respect to the intermediate output. Now what we observe is that this is very similar to the classifier guidance concept, but if we add this gradient information to all the pixel locations, then the guidance from any pretend facial recognition network introduces some artifacts for some regions. And as the diffusion framework is run for very large number of time steps, for example t equal to 400, these small artifacts accumulate over time, and at the end the perceptual quality significantly drops. So to keep a balance between the perceptual quality and also the identity specific feature, which is the guidance from the face recognition network, what we introduce is an spatially varying operation where we add an additional module which is a binary mask prediction module that automatically learns to identify the crucial facial locations that are important for the identity. So only for those regions we add the gradient information in a spatially varying manner to the intermediate output of the reverse diffusion step. And for the other regions, we let the diffusion model run free such that it can enhance the perceptual quality in an unconstrained manner. So we have basically two types of regions. For one, we add an additional regularizer from the face recognition network. For the other, there is no regularizer. So those regions can enhance the perceptual quality very freely. And this whole framework is trained on a synthetic dataset which is built using the FFHQ network, and we use the standard blind face restoration setting where you use different type of standard degradation such as blur, noise, downsampling, or JPEG artifacts, and so on. And for evaluation, we first test it on the synthetic setting, which is we take a Chellappa HQ dataset and try it on blind face restoration task for images of different resolution. And what we observe is that in terms of perceptual quality as well as identity preserving factor, which is denoted by the term IDS in the tables, our method achieves best results compared to previous state-of-the-art networks in most of the cases. Similarly, this is some qualitative examples where we observe that even if the input is of pretty bad quality, our output is much more closer to the ground truth in terms of perceptual quality or the recovered identity. We also visualize for some real examples, and we do not have the ground truth, so only qualitative examples are shown in the figure. And we also test it for very extreme upsampling or super resolution cases, and we observe similar performance improvements. These are some qualitative examples for the extreme upscaling cases. And not only like enhancing the perceptual quality, if we verify the downstream face recognition accuracy, which are built upon a particular subset of Breyer and LRFID dataset, which are real-world turbulence dataset, we observe significant improvement in terms of top 1, top 3, or top 5 face recognition accuracy using an pretend arc face network. Now, in terms of network ablation, this example shows like if we run for 1000 time step, which is row 2, the identity of the person significantly alters, which does not happen in our case due to the guidance from the IPC network. And also, this example shows some few cases of the spatially varying binary mask and also the output of the IPC network, which is shown in row 3. And if we introduce this face recognition loss to the unit, then it introduces some artifacts. And in future, we can further reduce the time step required using distillation loss.